Good morning, everyone. Let us start this session. So, during the last lecture, we have seen how to represent a force in a 3 dimension. So, that is called as a space force, and how to take the moment about the given point. Today, we will see the calculation of resultant for the space force. So, in the space force system, again, we have 3 types. One is a concurrent, second is parallel, and third is the general. Okay. So this is similar to the force in a 2 dimension. So let us see how to find out the resultant for the concurrent force system. So we have already studied what is the meaning of concurrent force system. So if the line of action of all the forces passing through a single point, then it is called as a concurrent force system. So here in the example, there is one vertical rod OA. So this is the point O, and this is the point A. So this vertical rod is supported by 3 cables. One is cable AD, second is cable AB, and third is the cable AC. So each cable has some tension, and that tension keep the system in the given position. That is, our rod OA is vertical. So point A is the point of concurrency. So the tension in the cable AD So this is the direction of the tension AD. This is the tension AB. And this is the tension AC. So question here is given. Determine the resultant of the system, and one condition is given. That condition is the resultant of the system is vertical. Okay, and also we have to find out, determine the tension in the cable AB and AD. That means we have to find out the tension AB and tension AD. Okay. So out of the 3 tension, one value is given, which is the tension AC. And this is given as a 20 kilonewton. Okay. And we have to find out these remaining 2 values, tension AB and AD. For that, condition is given. The resultant of the system is vertical. So when the resultant is vertical, that means the resultant will be acting along the y direction. And therefore, the x component of resultant, that will be 0, and the y component is 0. So first we will see how to find out the resultant in a 3 dimension for the concurrent force system. So resultant R bar for a 3 dimension, or for the space force, it is given by the vector addition of all the forces. So F1 bar plus F2 bar plus F3 bar, so on. So just imagine one general condition. This is the concurrent point. And there are different forces passing through the point, which is F1 bar, F2 bar, F3 bar, F4. This point is O. So for this system, if you want to find out what is the resultant, suppose we replace this system by a single force, and this single force is nothing but the R bar. So this R bar we can find out by this vector addition, F1 bar plus F2 bar plus F3 bar. So here we have to use the same concept to find out the resultant of the given system. So in the given system, there are three forces: tension AD, tension AB, and tension AC. So first we will find out the vector form for this tension AD, tension AB, and tension AC. So tension AC is only given value. So first we will write the tension AC in the vector form. So formula is F bar is equal to mod F into unit vector. Okay, so similarly we can write the tension AC as tension AC bar. This is equal to mod tension AC into unit vector along the AC. So tension AC, its magnitude is given, which is equal to 20 km. We have to find out this unit vector in the direction of AC. So first, find out the coordinate of the point A and point C. So here this is the origin. This is the z-axis. This is x-axis, and this is the y-axis, which is along the rod AB or AO. The point A, its coordinate will be, as it is along the y direction, its x coordinate is 0 and its z coordinate is 0. So measure the distance along the y direction. So it is 48 meter. So y coordinate is 48. So for the point A, coordinates are 0, 48, 0. For the point C, C point is lying in the xz plane. So its y coordinate is 0. Now measure the distance along the z direction. So along this z direction, so actually this is negative z direction and distance is 24. So it will be minus 24. So z coordinate is minus 24 and x coordinate. So measure the distance along the x direction. So that distance is given as a 16. So this is 16 and it is along positive x direction. So it is plus 16. So coordinate of point C are 16, 0, minus 24. Now you can find out this unit vector AC. So this is equal to, so you can consider this is x1, y1, z1, and this is x2, y2, z2. So our formula is x2 minus x1 into unit vector r plus y2 minus y1 into unit vector j plus z2 minus z1 into unit vector k upon the magnitude of that position vector. So actually this numerator, it is the position vector and divided by magnitude. So it is a x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. So put the value of x2 and x1. So x2 is 16 minus 0 plus y2 is 0 minus 48 plus z2, it is minus 24 minus 0 and this square. So it is 16 square plus 48 square plus 24 square. Okay, so calculate this value and then use this formula. So tension AC bar, this is equal to mod is 20 into this complete unit vector, which is a EAC. So finally, you will get the value for tension AC, which is a vector 5.712 unit vector I minus 17.136 j plus, sorry, this is minus 8.568 k. So this is the vector form for the tension AC. Similarly, find out the vector form for the tension AB and tension AD. Now for tension AB, we have to find out the coordinate of the point B. So for the point B, its y coordinate is 0. Its z coordinate is 12 meter, which is along the z direction. And x coordinate is 16. So for the point B, we have 16, 0, 12. Then for the point D, so D, it is on the x-axis. Okay, so its z coordinate is 0. And again the point D is in the xz plane. So y coordinate is 0. So it will have only the x coordinate and it is on the negative side. So it is 14. So it is minus 14, 0, 0. So for the point D, we have minus 14, 0 and 0. Okay. And then you can write the unit vector. So unit vector AB and unit vector AD. Okay, so get this unit vector. So directly I will write the unit vector. So whenever you calculate the unit vector AB, consider A point as a point 1 and B point will be x2, y2, z2. Similarly, for the AD, D point will be x2, y2 and z2. Okay, and use this formula. So this is your basic formula to find out the unit vector. So this unit vector AB, so this value is 16i minus 48j plus 12k upon 52. Then unit vector AD, so this value is minus 14i minus 48j and 0k upon 50. Okay, and then find out the vector which is the tension AB bar. This is equal to mod tension AB into unit vector AB. So here mod value is not given. So we will assume the mod of tension AB. It is just tension AB. Okay. So that complete vector you will get as tension AB bar is equal to this tension AB into 0.308I minus 0.923J plus 0.231K. And then write the vector tension AD. So this is equal to mod tension AD into unit vector AD. So this vector is tension AD bar. This is equal to, this is minus 28I minus 0.96J and its Z component is 0 for this vector. Okay. Now use the formula for resultant. So resultant will be, which is R bar, this is equal to, so there are three forces. One is the tension, AB plus tension AC plus tension AD. Okay, so tension AD is completely known value. Sorry, tension AC is known. Okay, so put all the values tension AB bar, tension AC bar, and tension AD bar in this equation. So for the resultant, this R bar we can write in the vector form like this: X component into unit vector plus Y component Ry into unit vector J plus Z component Rz into unit vector K. So this is general vector form for the resultant R bar. So we can put this value in this equation. So you will get the equation as Rxi plus Ryj plus Rzk, and this is equal to, now put this value tension AB. So this complete value. So this is equal to 0.308 into tension AB unit vector I minus 0.923 tension AB unit vector J plus 0.231 tension AB into unit vector K. Then tension AC. Okay, so this is tension AC. So plus 5.712 unit vector I minus 17.136 unit vector J and minus 8.568 unit vector K. So this is tension AC, and then put the value of this vector tension AD. So this is equal to minus 0.28 tension AD unit vector I minus 0.96 tension AD unit vector J, and Z component is 0. Okay. Now from this equation, just take this I common. So you will get value 0.308 tension AB plus 5.712 and minus 0.28 tension AD multiplied by unit vector I. Similarly, refer the J terms. Plus in the bracket minus 0.928 tension AB minus 17.136 and minus 0.96 tension AD into unit vector G. And there is one more term which is the K term. So just I will write here plus 0.231 tension AB minus 8.568 into unit vector K. Okay. Now here we have to equate the left hand side and the right hand side. Okay, so equating the LHS and RHS coefficients. So Rx value, this is equal to Rx is the coefficient of unit vector I. So this complete value, it is the coefficient for unit vector I on the right hand side. So this is equal to 0.308 tension AB plus 5.712 minus 0.28 tension AD. Then Ry, this is equal to Ry is the coefficient of unit vector J. So here, this is the unit vector J. This complete value, it is the coefficient. So minus 0.928 tension AB minus 17.136 minus 0.96 tension AD, and RZ coefficient of K. So this is complete coefficient of K on the right hand side, 0.23 tension AB minus 8.568. Now refer the given problem. So one condition is given. The resultant of the system is vertical. It means that the resultant may be vertically upward, that is along y direction, or it is vertically downward. So when resultant is vertical, its remaining two components will be zero. Right now the resultant is along the y direction. So its x component and its z component, these two values are zero. So you can write here, as the resultant is vertical, that is along y direction. Its x component, that means Rx is 0 and Rz is 0. And the complete value of resultant, that is complete R bar, it is just Ry into J. It may be positive or negative, but the complete resultant, it will have this format, as its x component is 0 and the z component is 0. So you can refer this general formula, as this is 0 and this is 0. So resultant will be just Ry into J. Okay, so Rx is 0, Rz is 0. So you can put the value here. This is 0 and Rz is 0. Okay, so from these two equations, first you can find out this tension AB. So equate this complete equation. This is 0. So calculate the tension AB. So tension AB, this is equal to this is 37.09 kilonewton. And from this equation, put the value of tension AB. You can find out the tension AD. So tension AD, this value is 61.12 kilonewton. And now put the value in the Y component. So this Y component, it will give the value of the complete resultant. So put the value tension AB, tension AD, and get the value of Y component. And Y component is nothing but the Ry. So first, get the value of Ry. So Ry value is minus 110.05, and the resultant R bar in the vector form, this is equal to minus 110.05 into unit vector J. So as the value is negative, that means the resultant is acting in the y direction, but it is vertically downward. So this is the correct direction for the resultant. So this is your R bar value. Okay. So in this way, you can find out the resultant for the given concurrent force system. This is your basic formula. So resultant in a 3-dimension or in the space force system can be represented as a vector addition. Okay, now refer the next system, which is the parallel force system. So here we have one horizontal plate, which is a OA, BD. On this plate, there are 5 forces, F1 to F5, and all the forces, they are acting parallel to y direction. And question is, we have to find out the resultant for the given system and its position with respect to the point O. So find the resultant and its position with respect to the origin. So your first step, resultant R bar, this is equal to the vector addition for F1 bar, F2 bar, F3 bar up to F5, as there are 5 forces in the system. Now for the parallel force system, just consider a single force. Okay, so this is one 3-dimensional space. This is X, Y, and Z. And there is one force in this 3-dimensional space, which is parallel to Y axis, like this. Okay, its magnitude is given as a 50 Newton. And force is acting at a point A. So this is 0, 1, 0, and 2. Okay, so this is the coordinate of the point A. At this point, force is acting parallel to y direction, 50 Newton, and it is along the positive y direction. So its vector form we can write as F bar is equal to the magnitude is 50 and just multiply by the unit vector along the y direction. So along the y direction, unit vector is j. So this is the vector form. The remaining 2 components for this force will be 0. Fx is 0 and Fz is 0. Okay. So this is the vector form for the parallel force system. Suppose there is one more force which is parallel to x-axis, like this, and its magnitude is 20 Newton. So its vector form we can write F bar is equal to magnitude 20 and multiply by the unit vector along the x direction, because force is parallel to x direction. So unit vector along x direction is I. So 20I is the vector form. So we have to use same concept for this system, so that we can find out F1, F2, F3, F4, and F5. So I will write F1 bar. This is equal to force F1. Its magnitude is 3. It is parallel to y-axis. So unit vector along y-axis j. Observe the direction, whether it is positive y or negative y. So this arrow is vertically downward. So it is a negative y. So it is minus 3j. This is the vector form. Same for F2. So F2 bar is equal to 5 kilonewton into unit vector along y direction. So it is a 5j, and it is in the negative y direction. So it is a -5. Then F3 bar, this is equal to, so this is 6 unit vector j, and it is negative. Next F4, so F4 is 2 kilonewton. It is parallel to y-axis, so unit vector j, and it is positive y direction, so it is plus 2j, and F5, this is equal to -7j. Okay, so now we have represented all the given forces in the vector form. Next step is we have to find out the resultant. So for the resultant, so resultant R bar, we have to use this formula for the resultant. So just add all the vectors: -3j, -5, -6, +2, and -7. So this resultant is -19, and unit is kilonewton. Okay, so this is the resultant for the given system. Now next step is we have to find out the position with respect to point O. So when we find out the resultant for any system, actually we are replacing all the forces by single force. So let us assume the resultant of the given parallel force system is acting at this point. So right now we don't know the exact location. So just I will assume this point to be point M. Okay, so this M point, it will have the coordinates X, Y, and Z. So we have to find out this coordinate. Okay, so definitely it's for this point, its Y coordinate will be 0. Okay, but we have to find out this remaining two coordinates. So this distance, this is nothing but the X value, and this distance, it is the Z value. Okay, Y is 0 because the point M, it will lie in the XZ plane. So this is the XZ plane. Okay, so for any point in the XZ plane, its Y coordinate is 0. So now we have to find out what is the X value and the Z value. So to find out this, so actually this is resultant, which is the R bar. Okay, I have taken the resultant in the downward direction because from the calculation we got the resultant as a -19g, and it is a -19 means it is negative direction. So here we have to use the Varignan's theorem. Okay, so by using the Varignan's theorem, we can find out the position for the resultant. So Varignan's theorem is summation of moment by all the forces about the point O. This is equal to the moment by the resultant about the same point O. Okay, so for the summation of moment, we have to refer the original system, that is the system of forces. So in the system of forces, the F1 is acting at the point O, That means the line of action for F1 is passing through the point O. So its moment is 0. For remaining component, that is remaining forces, F2, it is acting at point A. So we have to take the moment by the F2 about the point O. So we have already seen the formula for moment. So just I will write it. So suppose we have the point O and it is having the coordinates. Let's take, this is the force A bar. The force is passing through the point which is A, which is x1, y1, z1, and this is x2, y2, z2. Okay, and this point O is x3, y3, and z3. So its moment, that is moment by force about O. This is given by this determinant I, J, K. Here we have Rx, Ry, and Rz, and this is Fx, Fy, and Fz. So Fx, Fy, Fz, these are the component of the force, and Rx, Ry, Rz, these are the component of the position vector. So here we have to find out this position vector. So position vector O to A. Okay. So we have to use the same concept to find out the moment.